All right, welcome back, everybody. So I'm just going to the data simulation algorithms that are available in JEDI, at least some of them, and also give a few reminders based on the various questions we've had so far, because I think maybe these are things we should have addressed early on. So first of all, some basic data simulation reminders. Numerical weather prediction is a cycling process, so it's repeated every few hours, typically every 6 hours for global forecasts, so 4 times a day, and more frequently for local forecasts. And for that, the period over which we use observations is called the assimilation window, and this overall process is called the cycling. Now, I just wanted to clarify that the cycling algorithm is really something that's coded in scripts and in workflows. And a typical cycling data assimilation system is made of hundreds or thousands of tasks per cycle. So these are all independent executions that will run on typically an HPC system and be coordinated by some workflows and some script and that can control in which order they run, and when the output of a task is used as an input for the next one, and etc. And the data assimilation itself, as we see it in JEDI, is happening in one or possibly a few executables. And so the whole cycling algorithm, if you want, is something we are developing at the Joint Center, but it's not included in the initial release of JEDI because it's not finished yet. And it's not something we cover in this academy because the code is not there, so we can't really show you how to use it. So this academy really only covers the data assimilation algorithm itself, and that's why things like how to generate an ensemble is not really covered in what we are showing you this week, because it's more at the script and level how you would have an ensemble system, an ensemble data simulation running that generates an ensemble forecast that's then used as a background to compute your flow-dependent B matrix. But that's outside really of the data simulation executable, and that's why we are not covering it at this point in what we are showing this week. That will come in the future, but that's probably needs another 6 months or a year before we can make that available. Okay. So another reminder about how data assimilation works. Typically, we have an assimilation window and we have a previous forecast, which we call the background over that assimilation window. Then we have observations over that window. So again, typically for a global forecasting system, that would be 6-hour window. Then from these observations and the previous forecast, we can compute the differences between the forecast and the observations over the window. And by minimizing that difference, we can compute an analysis, which is the best estimate of what the state of the atmosphere or ocean or whatever system we are looking at is, given both the previous forecast and the observations. So that can be a complex process, but that's really is the idea here of how the assimilation works. Now, that's a 4D assimilation algorithm. So typically something like 4D var, 4D and var would work like that. Now there's also something that was used in the past that was a 3D assimilation process where basically we ignore the time dimension and everything from the previous forecast. We only keep the value at the middle of the window and we ignore the rest of the forecast. all the observations are moved also at the middle of the window, and the analysis is the best on that completely all the time aspects. As far as I know, this is not used anymore in operational systems, but that's an algorithm that has been used in the past and might be used for some academic studies. There's another intermediate way to do the assimilation, which is called the 3D FGAT, so first guess at appropriate time, where the difference between the forecast and the observations is computed, taking into account the time dimension. And then the previous forecast in the middle of the window is kept. And this time, instead of bringing all the observations at the same time, they're all kind of leveled around the background in the middle of the window. So this time it's not the observations themselves that are brought back to the middle time, it's just the difference between the forecast and the observation. So it's a little bit more accurate. And that is still used in quite a few places, and for ocean data simulation, but also for atmospheric systems in some places. So this is the 3D VAR, 4D VAR, and 3D FGAT that you've seen or heard about in some of the YAML files and some of the exercises that you've been running. Without the 3D or 4D ENVAR version, which is just a way to specify the background error covariance matrix. All right. So I'm now going back a little bit to how the design of OOPS and JEDI came about. So again, we have previous forecast background and some observations. Now we can also include in the data assimilation process some other information, like theoretical information. So things that the physics is telling you that you can write as additional constraints, and you can consider that as another source of information if you want. So here I've written something that you've seen before. An example was the variational data assimilation cost function, where you see the first term, that's the background, what's called the background term, with a B matrix that's represented with bump, for example, as you saw this morning. And then the second term is the observation term with the H operator, that's the observation operator that we've talked about already many times. And here you see a sum over from 0 to n, which represents the times within the assimilation window. I'm assuming things are 4D here. And the xi, which is the state at different times within the window, is usually computed through running the model for that window, and either you do that online in core in memory, or you can run it ahead of time and read in from files. Obviously, if you do it from files, it's more I/O, which is going to be less efficient, and it also limits what you can do to solve that problem. So that's something that really we would like to move away from, but that's more of a scientific question than technical. So to design the code really to do all this in a generic way, there's been a number of considerations that were taken into account in the initial design of OOPS and JEDI. So how we can design this cost function? So the first approach, if you think with what you've heard about object-oriented programming and C++, you want to define one object for each term of the cost function. You compute each of these terms, or their gradient if you need to, and then you add them together to form the full cost function. That seems kind of fairly reasonable. However, the problem is that the model is going to be run several times, because you need the state of the atmosphere at several points in time in your window, once in the observation term, once in the JC, which is a constraint, typically something for initialization, like a digital field. You can have a modular term as well, which I wrote as JQ here, but all these things, you need the model. And if you really make your terms of your cost function independent, means you're rerunning the model several times, and that's fairly expensive, so you don't want to do that. So the other approach would be to run the model once and store the full 4-dimension state. And then you can compute each term of the cost function based on that. So you have your x, what I was denoting as xi on the previous slide, all in memory for all the i's from 0 to n. And then you compute each term of the gradient and add them together. Now that's also, on paper, something that looks good. The problem is it's way too big. Like, there is no way you could store on any existing supercomputer a full 4D state at operational resolution and at every time step of the model. It's just not possible. So, so really the feasible approach there is you want to run the model once. There is no question about that. And so the only option, if you don't want to rerun the model or store the 4-dimensional state, is to compute each term of the cost function as the model is running. But that's the only way you can really do it efficiently. And then you add all the terms together once the model is finished running. So, so this is what is done in JEDI. There is still one class for each term of the cost function, but then each term of a cost function is a post-processor. So you've heard about these post-processors before, and they are either the term of a cost function is itself a post-processor, or it kind of creates one that it can attach to the model. And when the model is running, this post-processors will do their job and compute whatever is needed from the model state at that time, store it somewhere, but they don't need to store the full state this time. They just store whatever they have computed from it. And at the end, we can finish all that, and the cost function can sum all these terms together, and that's how we compute the cost function. So this concept of post-processor for the model is really quite central in everything we do in JEDI. A few more details about the cost function. So there is a base class for the cost function, which is abstract, and then there are subclasses. There is one for 3D var, one for 4D var. There's one also for the weak constraint 4D var. There's one for 4D and var. Now you will see, if you look really carefully at the code, that if you choose your parameters wisely, you can reproduce 4D var with the weak constraint 4D var cost function and 3D var as well. However, many people thought that to learn the system, it was easier to have an explicit 3D var code in there that we can look at and understand before going to some more complex ones. So we kept them just because of the readability they provide. Now, the terms themselves of the cost function, they can be reused. So like, for example, the JO term, the observation term, is reused in both the 3D var, the 4D var, and most of the other ones. And for example, the 4D and var was added in just a few hours. It's fairly simple. It's just recombining various pieces slightly differently. So that's really where this system shines, is that it's very easy to reorganize various terms of a cost function to create a new cost function, something that is usually very difficult to do in a system like a GSI or the IFS or any of the other existing Fortran codes where things use global variables, so you cannot really change the order in which things are computed, because that would change all the global variables and nothing would work anymore. However, So it solves the technical aspect, but it's not going to be a magic solution to all your scientific questions. So you still have to do some science. I guess most of you are scientists, so that's what you're interested in. So the idea really of this design is to make it easier in terms of the coding aspect, so you can focus on the science. So there's a little bit of learning to do to really understand a system like JEDI, but I hope by the end of this week you will be able to do some basic science with it, or at least in the week or two after, and you can try to remember the first time you used GSI or an operational system, how long it took you before you could really understand how it works, and it's probably counted in months, if not more. So hopefully, once you know the system, but it will be a lot easier to do new science. So post-processors, I think it's something we've mentioned that before, that really the idea is to separate is separation of concerns, as we've mentioned many times, and it's to separate the model from the data assimilation. And it's in fact doing more than that, and it's separating the model from all kinds of actions that can happen while the model is running. So like the output of forecast fields should be done by a post-processor, generation of products, computation of a filter state, as I said, for digital filter initialization. We've already talked a lot about the simulation of observations that's happening during the model run. The generation of a trajectory for a tangent linear and adjoint model is also a post-processor that's saving whatever it needs from the current state to generate a trajectory. All kinds of diagnostics can be seen as post-processors. So hopefully in the future, a lot of these kind of tasks that go around the model can be extracted from the model code itself. So the model code can be really the model, and people can focus on that, and all these auxiliary tasks can be performed by post-processors. That would be the idea. If there was some people wanted to take this concept a bit further with some models and try to really bring the object-oriented approach inside the model, I think that would be great for future models. It's a little bit difficult to do for existing ones, but there's really room there for doing a lot more with the generic approach and the reuse of code for in the model itself, if people wanted to in the future. But at least for the data assimilation, that's what we're doing in JEDI. All right. So what I'm going to show next here is this is a YAML file for 4D-var. This is the way we envisage it will look in the future once we're done with this this tool I mentioned already several times. So so you can see here. You have a 4D-var, that's the cost function you want to use, a window length. The beginning of a window here, it's not defined explicitly, it's just a template basically, because when you're running an experiment with cycling, this date is going to change at every cycle. You have a different date, the date is moving, so you can't specify it explicitly here. And then what you see in many places, like you have a geometry and it's just this dollar parenthesis geometry, so that this syntax might change. It's something we came up with, but basically what you will do is this is the general YAML file for a 4D-var, and then we want to provide a tool where you choose a model you want to run with, and depend if you choose a Lorentz model or QG or GFS or MOM6 or whatever other model, it will kind of then go and fetch the correct geometry definition and model parameters and etc. for that given model. Same thing for the observations. There's a dollar parenthesis observations here, which will be then we provide a tool that will go and you'll probably have a list of observations, and you kind of click which ones you want to use, and it will go and fetch the correct sections of YAML to fill in that section here. And then you have a few things that's stay here, like the minimizer that you want to use in your 4D var, number of iterations. So that's not model dependent, so you can specify it here at the level of the 4D var code. The linear model will be defined by a tool. Now, if you want to go from 4D to 3D var, there's not a lot that changes here in this YAML file. You change the cost function at the top here, 4D var becomes 3D var, and you just remove the model and the linear model because they're not needed in 3D var. But the rest really stays the same. So I know at the moment the YAML files are a bit long, but if you start thinking of them in that way, that and try to abstract a little bit what is specific, what is generic, they become a lot simpler, even though they're a bit long. Same thing for the FGAT. It's actually the FGAT you would do by running a 4D var. You leave the model as it is, but you replace the linear model by an identity, which is generic. So you can do it here. It's not model specific. So I hope that thinking of the YAML files in that way will help you understand a little bit how they are structured, and also they help you understand how the things should align in your YAML file. So what's the first level in the cost function is indented once, and then what's inside geometry, inside model, etc., is indented one more time, and that can go like that, be nested as needed. One trick also, still about the YAML files, some editors, when you edit a YAML file, they let you open and close the section. They put this arrow on the side here, like for example for background error, and if you click on it, you expand it, and if you click again on it, you close it. So that, again, that really helps you when you're editing your YAML file to see the different levels and to dig, open only the parts that you really want to focus on and go deeper in the YAML structure without having to see everything all the time. And so this example here is with an editor called Atom, but there are other editors that do that, and they let you fold and unfold the different sections in your YAML. So I would really encourage you to use an editor that has that capacity if you want to work more with the YAML files until we have a better tool to handle those. All right, JEDI applications. So the JEDI applications are found in the OOPS repository, in this source OOPS run. And for example, you have there the variational.h, forecast.h, hx.h, a bunch of other ones. This is the normal way of using JEDI is to run an application. What you do when you're using the C-test is really, these are special main programs that manage the test and add reporting for the test. In principle, most of you will never really have to look into how this technical aspect of the test is working. And really you should focus on the applications. That's the important part. But yeah, for your day-to-day work. And even if you want to add a test, in principle, you don't really need to go into the technicalities of how all this testing is working. So, try to, if you find the system a little bit overwhelming, start with one application and really focus on that to get started with the system. So in terms of variational data simulation, there's several cost functions that are available. They're all in the same application, the variational.h. So there's a 4D var, 3D var, 4D EN var, we constrain 4D var. Note that the last two, so the 4D EN var and the constraint 4D var, they are parallel in time. So when you, in your 4D EN var, you read in the state at different times. And that's done on different MPI tasks in parallel. So that's a little bit more efficient, and same thing for the weak constraint 4D var. So you don't see the loop over time really in the code much because it's kind of handled by MPI. We also have a whole lot of minimizers available for this variational DA. They exist in primal space, so the model space. So that's the X, if you want, in the custom in dual space, so in observation space. So that's something that's often used for ocean data simulation because there are relatively few observations in ocean systems, and that makes the vectors for doing the linear algebra a lot shorter and a lot smaller, and so the code is faster that way. There's also, I don't know how to call it, this double primal space minimizer. So that's what's used in GSI. That's what's called the Derber-Rosati algorithm that doesn't need the inverse of B, which is nice because that's typically very ill conditioned and you don't really want to compute that. And there's also a saddle point minimizer that's kind of a combination of primal and dual space at the same time. No, that's only really for the weak constraint for the Varfis one. And within each of these primal, dual, or this Derber-Rosati space, you can have several algorithms. Typically, we have a preconditioned conjugate gradient length choice algorithm. The whole bunch there. You can go in the code and have a look if you're interested. But that we cover a whole range already of minimizers, and I think that's a fairly exhaustive list of what exists in variational DA. And that's all controlled by the YAML file. So typically what I showed before is the, okay, I can go back. No, you just change this just one line to specify PCG and shows GMRs, etc. It's very easy to change. All right, there's also something called ensemble applications in the same directory. And that's an interesting application, but it's templated on an application. So so you run this ensemble application with another application, and it will just run an ensemble of that application, whatever it is. So it's a really generic way of running an ensemble of applications in the same executable. The YAML file is very simple. It's just a list of the YAML files you would pass to each member of your ensemble. So, so for an EDA, for example, you would just pass the list of, so here it's 3D vars, you just pass the list of 3D var YAML files, and it will look at how many there are in this list and generate an EDA with 4 members here in that case, and pass the correct configuration to each of these members. So the EDA really, in JEDI is coded at 77 lines of C++, and that includes the comments and a few YAML files. But that's really simple to do an ensemble application with that. It works with ensemble forecast, ensemble of HRX, all the other applications should work. I don't know if it would work to actually make it recursive and pass an ensemble application to the ensemble application, but maybe that's pushing it a little bit, although it might work. So the only constraint there is that all the members have to run the same application because it's templated on one application. So you cannot have like one assimilation and one forecast and one H of X. They have to be the same application, but they don't have to have the same configuration. So you can just with that do an EDA where you have some members that are 3D var, some that are 4D var, some that are low resolution, some that are high resolution. It's really a very, very flexible system. And again, just very few lines of code to achieve that. So that's a really nice tool. Finally, there are many more applications available in there. I didn't, so I've listed, I think, the ones that are there now. You have this local ensemble DA, that's for LETKF type of assimilation, if you're interested in that. And there's a few things here. Some are still in development and they're not documented. Some are not supported, but feel free to explore if you're interested in some of those things and want to see how they're done and how they work. some of them can be quite instructive in how they're done. Okay, and that's my last slide, working with JEDI applications. Really, all the applications in JEDI are generic, and given the appropriate YAML file, will work with any model. That's very important because really the way you should be working with that is when you want to develop something, a new application, is you can debug and validate it with very simple toy models. It makes it much easier to debug. It runs super fast. You can run with Lorentz of a QG model on your laptop. You don't need to sit in a queue on an HPC system. And then you apply it to a real operational model. I know there is this thinking in operational centers that you should not work with toy models because it's a waste of time. In this case, it's not, because you're coding something and testing it with your toy model, but you don't need to recode anything. You just change your template as we've shown, your trait, and it will run with a real model. So you can save a lot of time on your debugging by working with these toy models, and it also helps you to understand the algorithm. So I would definitely encourage you to do things with toy models when you can as a first step, because it will make your debugging much faster and much easier. And we provide two toy models really with OOPS, the Lorentz 95 and QG models. So use those for that. They're also a good place to look into if you want to understand how the interfaces work. Look at these toy models, look at how they're done, how they're coded, how they work. It's a very good way to learn before you dig into something as complicated as FV3, which is a lot more complicated, a lot more difficult to understand. But if you have already a good understanding of how the simple models work, it gives you a really good starting place to understand the more complex interfaces. So I will stop there. So it wasn't all about the algorithm, but I think there's some, given the questions we've had in the last few days, I hope that will help you get into JEDI a little bit easier. I'll stop there and take questions.